Welcome to Chapter 17 of sdm4. This is entitled Sampling Distribution Models, and it's important to take a deep breath here. We're really shifting gears pretty dramatically. First parts of the book, we're really thinking about how to understand data, thinking about univariate and bivariate relationships. The next part moved into this idea of sampling and observational studies versus experiments. The next part was really much more theoretical. There really wasn't much data, there really wasn't much R involved. But it was allowing us to kind of posit probability models that could be used to make sense of the world. The idea of sampling distribution models is really critical to statistics, and it's a place that often ends up with some confusion for people. Because the idea of a sampling distribution is hypothetical. It's like taking all possible samples of a particular sample size. So as you proceed through this, keep in mind this idea that this is a concept, not something that's really tangible. But we'll try to make it more tangible in class and in some other ways through these examples. But it really kind of introduces an idea, the central limit theorem, which is pretty amazing. So the chapter starts off with the idea of sampling distributions of proportions. We think about, say, flipping a coin a certain number of times. And this is kind of being used for examples of smoking status for people in the United States. And then, even though we don't need to do it, we will utilize some kind of normal approximation to this. So what we were thinking about in terms of the normal approximation to the binomial is very relevant here. I'll show you in a few minutes how we don't need that anymore. We can actually be using the exact binomial calculations. But it turns out this actually works very well and actually gives us a good way of describing what this sampling distribution looks like. The normal model, the assumptions and conditions are outlined in section 2, and we talk about the ideas of independence, randomization, 10%, and success failure, and how this can be set up then in terms of these underlying probability. An example will do that. If any time there was a time to do the just checking, this would be the time to do it. And then thinking about the sampling distribution of other statistics. And what's really important here to think about is that for some other distributions, the distribution of the sampling distribution may not be normal, as we see here for the example for the minimums, and even for the variances. So the central limit theorem is really what could be thought of as the fundamental theorem of statistics, in the same way that we know that means are less variable than individual observations. That's really the law of large numbers. The central limit theorem tells us that the distribution of a mean is more normal than the distribution of the original underlying data. And that's said in a couple of different ways. And you want to make sure you're very happy with the idea that if we start off with a distribution that looks like this, and we repeatedly sample thousands of times from that of size, say, 10, we'll get a distribution that's more normal than the original data. If we look at larger sample sizes, those are going to be even more normal. And as we get to very large sample sizes, and this sample size is about 200, if we repeatedly sample thousands of times, we'll get a distribution that looks approximately normal. So there are, as always, important conditions. There's a good question about which normal it will be. That's all laid out in these examples. There's a very good step-by-step example provided, and then a kind of a summary. And as I said, this is a place where people often find complications, run into problems, and so it's very useful to go ahead and complete the just checking and think about the summarization, look at the places where things go wrong, and then finally the learning outcomes for this chapter. Doing this in R is actually kind of fun and pretty straightforward. We'll use the Mosaic package. So for example, we can describe these distributions by taking a whole bunch of random binomials. The random binomial, R binom, it's another one of these helper functions for statistical probability distributions. We'll take num_sim, in this case 2,000 different samples, each of size 1022, and with the true probability given by 0.57. So matching the example on figure 17.1 in the book. We can actually see what that distribution looks like. and we can actually generate what the normal underlying probability model would be under those assumptions. We can do the same thing for other statistics. Here we have for the medians, variances, and minimums, and again we see that those distributions don't end up being as normal. It's lovely, the central limit theorem, starting with a single observation and then thinking about 10, 50, or 100, and finally ending up 200 with the distribution looks pretty normal. You'll notice I'm actually kind of cleaning up my histogram a little bit by setting the width in the center, and these examples may be helpful in seeing how those are structured. And then finally we can repeat the calculations at the end. Example. So sampling distribution is an important precursor, what we're going to be doing when we flip things around. Up until now with probability we know all, and we kind of see what the probability of something is. Pretty soon we're going to be going around now assuming a probability model, generating some data, and using that to infer what our population parameters would be using these probability